Hi, my name is Jonas and I'm a hardware technical lead for Vortex NTNU. And this is Beluga, our newest AUV. This AUV has been in the works for 2 years now, and I'm really proud to show you the result of all this work. Let's look at some more details about this drone. So, the first thing we're going to look at is the frame. The frame is made of polymer sheets, 10mm thickness, and it's been cut with water jet cutting. The reason we chose polymer sheets was mainly because of its strength, its ease of manufacturing, and also its corrosion resistance. Last year we used aluminum profiles for the frame, and we had really big problems with corrosion. The sheet is held together with angle brackets and corrosion resistant screws. Next thing we're going to look at is the electrical housing. You will find it in the top here, and it's made of 8-inch acrylic tube, and it has end caps from Blue Robotics. On the top you find a kill switch, which is magnetic, so when you remove it you cut the power for the thrusters. This is a safety feature that is important for the operation of this drone. One of the important systems for the competition is our actuation system. We have chosen a pneumatic system that is similar to hydraulics, but with compressed air instead of oil. We have 3 different manipulator systems. We have the torpedo system in the front, we have the gripper on the right side, and we also have a marker dropper that is tucked away inside the drone. All of these systems are pneumatic. The pneumatic valve housing is found in the middle of the drone. For localization and control, we mainly use 4 different sensors. Inside the electrical housing we have an IMU. It's a Sensonor STIM 300. In the front we have a Z2 stereo camera, and below we have a multi-beam imaging sonar. On the bottom we have a Nortec DVL, and we also have a downward facing camera for some of the specific tasks. Now I want to give the word to our software guys to talk more about how we use these sensors.
Hello, I'm Ivan, and I'm here to present to you the autonomous system strategy. The autonomous systems team has this year tackled the challenge of creating a general missions execution framework. The solution the team came up with is the so-called Search, Converge, Execute framework. It is a finite state machine structure created in order to facilitate simpler communication and design between the autonomous systems and perception groups. It acts essentially as a standard template or scaffold, abstracted away from any task specifics. In this way, when an autonomous systems member and a perception member get together to design a solution, they can simply discuss a meaningful search, converge, execute state pattern for the task, building their specific solution within the rigid scaffold. The transition between search to converge and to execute are governed by decision logic on the side of perception. To illustrate the system, an example is in order using the gate task. The gate search state involves performing a robust search algorithm, and transition to gate converge happens on declaration of gate existence by perception. The gate converge state involves estimating the full pole state of the gate, and transition from converge to execute happens on the state being declared estimated by perception. The execute state is aligning the drone perpendicular to the gate and driving through. For other tasks, these patterns are completely different. Note that perception not only provides logic from going from search to converge and to execute, but also from going back to search from converge and execute states, should the previous decisions be declared wrong. This has the goal of making the algorithm more robust. As a general competition strategy, we have chosen to prioritize tasks which are feasible. That is the inspection task, which do not use gripper. The wish here is to rather solve fewer tasks well, focusing on fundamentals and performing those before moving on to manipulation in the future. This can be seen as a trade-off between feasibility and task point weight, taking into account the workload and knowledge constraints of a student team.
Hello, I'm the perception lead at Vortex NTNU, Benjamin. The exteroceptive sensor stack of Beluga is designed so it can be used in a wide range of scenarios, as well as being sufficiently robust so that the group can continue to develop new software for it into the future. Beluga utilizes 2 cameras for the competition. First, a Z2 stereoscopic vision camera, which provides the drone with both RGB color data and 3D depth data. The second, a downwards facing camera located under the drone, is used primarily for path following and dropper tasks. This year, the perception team has come up with a general algorithm for solving the competition tasks. Vortex Computer Vision Pipeline. The CV pipeline, as we call it, is a modular framework which allows us to detect, classify, and estimate the pose of competition objects underwater. There are several complex processing layers that we perform to do this, from pre-processing, to object detection, to pose estimation, and its filtering. The core of the pipeline concept is to serially process the aforementioned sensor data by stacking the algorithms and reducing the data complexity with each step. This way, we are able to go from having depth plus color data to object positions in a generalized and observable fashion. This ideology has enabled us to be able to solve the gate, path following, bins, and poster tasks using almost identical classification and estimation methods. However, the detection methods differ, as neural net object detection is used for picture-based posters, although it is outperformed by color detection-based algorithms for abstract objects.
Hi, I'm Nicholas, member of the Acoustics and Embedded Systems team. The last problem we wanted to solve was finding tasks marked with pingers. For this, we needed a solution to determine either direction or the position of the pingers directly. The solution that we have come up with is based on time difference of arrivals. For this, we will be placing 5 hydrophones around the drone. These will be able to pick up the pinger pulses. The analog signals are then converted into the digital domain to be used for further processing on a microcontroller. There we can compute position estimates based on the time difference of arrivals. We can then average these estimates over time to provide a more accurate waypoint for the drone to move to. This provides the means necessary not only to get within the required distance for perception to take over on the torpedo task, but also place the drone reasonably accurate within the octagon for surfacing. And with this, we have covered all the elements we are going to attempt during the competition. Thank you for watching.